Hello, let's continue our Sudoku adventure with Orderly Arrows by Strosahl. So this is another duality puzzle. So instead of just treating these as a mash of rules, we're naming them the two common constraints that you'll encounter and treating those separately. And then it's applied to the same visual, so they overlap. And the reason we do that is because you may be familiar with arrows, you might be familiar with sequence lines. This is both. And so what I'm going to do is I'm going to explain each one separately, and I'm not going to talk about, in the rules at least, section, I'm not going to talk about how they might synergize, because that's definitely part of the puzzle, is to think about how do these two things work together and how does that restrict things. All right, anyway, with that said, we do have normal 6x6 Sudoku rules. That means in each row, each column, and each 2x3 box, we are placing the digits 1 to 6 exactly once each. We have circles in the grid that have attached arrows. Whatever digits go on the arrow, say this was 2 and 3, that they sum to the value in the circle. So that's 5. So if this was 2 and 4, that would add to 6, right? These two sum to that. If multiple arrows share the same circle, they're independent sums. So if this was 6, this could be 2, 4. This could also be, this could be 1, 5, and then this would be a 6. That would be one way to resolve this guy. They're independent. Just think about it as 3 different arrows that all happen to share the same cell for where their circle is placed. And in addition to that, every arrow is also a sequence line that includes its circle. A sequence line is a sequence of digits in order with a constant difference, like 1, 2, 3, 4, 5, 3, 1, right? So for example, 5, 3, 1 here, if this was just a sequence line, we know that that doesn't add correctly for an arrow. But 5, 3, 1, you can see that starting from any end, we have a difference of 2. So we subtract 2 and then we subtract 2 again. Or from the other end, we add 2 and then add 2 again. The constant difference can be negative. Like we said, we subtract 2, but it does not change sign. So we can't do 2, 4, 2 because that changes sign in the middle. We could do 2, 4, 6, but we can't do 2, 4, 2. All right, and the difference can be 0, so 4, 4, 4 would be a valid line. And just like the arrows, treat these as individual sequences. So this is a sequence like 6, 4, 2. And then this is a sequence also like 6, 5, 1. Well, sorry, like 6, 5, 4 would be another sequence. So the difference can be, they're separate clues, right? This sequence line, this is a sequence line, this is a sequence line. All right, anyway, that's it. Those are the rules. There's a link in the description if you'd like to try the puzzle yourself. And I'm going to get started right now. Okay, I want to think about how sequence lines interact with the circles. We know that it's not a difference of 0, except for this one. This one is a difference of 0, but this is just a clone cell. That's not a big deal. All these other ones, they can't have a difference of 0 because how can we have 2n equal n? We don't have 0, right? If we had all zeros, maybe, but then, I don't think any of these can do that just because it's Sudoku anyway. But we don't have 0, so we can't do that. And so we're going to have a difference of at least 1. And if we think about it, this is going to be the same. So there's going to be essentially the same base in each of these. And we know it's going to increase from here, 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 because this is the largest digit. The circle is always the largest digit of an arrow. So because we're going to increase, whatever this base is, this is going to be the base plus our constant. And this is going to be the base plus 2 times our constant. So the total sum is going to be 3 times our base plus 2 times the constant. That's going to be the total sum of all the... Anyway, I don't know if that's helpful, but that's interesting, right? I'm trying to do some algebra here. And so... We could definitely do 1, 2, 3. But that's the only way we could have the lower digit be 1. And then we could have 2, 4, 6. There's got to be some... How do I think about this? Feels like those are the options. 1, 2, 3 or 2, 4, 6. What is it about that? So the sum, okay, maybe we can think about the algebra a little bit differently. The sum is going to be the sum of these two, which is going to be 2 times the base plus our constant. So 2 times our base plus our constant is equal to, is this guy, but that's also equal to our base plus 3 times our constant. So why don't I just pull out my little pen tool here? Wait, let's do some algebra, and forgive my handwriting, mouse handwriting. My normal handwriting is already bad, and this is my mouse handwriting. But what we're saying is that in one way, because of the arrow, we know that the sum is going to be 2 times our base plus 1 instance of our constant. And then that's going to be equal to, because the circle is also, just because it's a sequence, it's going to be our base plus 3 times our constant. And so we need solutions to this. We can put each one on each side. So this is going to be base is equal to 2 times the constant. That doesn't seem right, does it? That doesn't seem right at all. What did I do wrong here? No, it's because this is 2 plus 2. Sorry. Right. It's not 3. It's not 3 times the constant. It's 2 times the constant. We only add the constant twice. So B equals C. That's what I was. That was the vibe I was getting here. But yeah, that proves it. So the only way that's going to be true is if B equals C. And so that's why it had to be 1 with a constant of 1 or 2 with a constant of 2. If we did 3 with a constant of 3, we'd go 3, 6, 9, which isn't going to be possible in this puzzle. So we've just proven that the only way any of these arrows work, the 2-cell ones at least, is to start with 1 or 2 and then go to 2 or 4 and then end in 3 or 6. And this is the same as this digit. And I could have done it here as well. So we have some pencils in there. And then, so this is a 3-6 pair. Is that interesting? So we know that whatever this is the other one. Interesting. Is there a problem with doing, I don't know. So we know that these two are the same digit. And we know that these two are the same digit as each other. And we know that these are the same digit as each other, and they're all different. And then we know that this is different from all of them, because none of these can be 3 or 6 if they're the other one. So this is going to be our red digit. And so then this is the other one that isn't. So this is, oh, interesting. Oh, sorry. We just have a 1-2 pair right here. No coloring necessary. Okay. 1-2 pair here gives us the 4. And that makes this 2, 4, 6, 4, 2, 6. That makes this 3, 1, 2. And that makes this 4, 2, 6. All right. Now it's just Sudoku. Perfect. So thinking about the algebra actually helped. This was a algebra question disguised as a Sudoku. All right. That's fun. This is just 1, 2, 3. Oopsie, wrong mode. Ooh, very bad. Okay. This is just 1, 2, 3. This can't be 2 or 3, right? Oh, why am I saying 1, 2, 3? Sorry. This is 1, 3, 5. What am I doing? This is 1, 3, 5. That's not 3. That's not 1. This is 3, 5, 6. So the 3's in one of these two. This is 5, 6. This is 3, 5, 6. Where's our Sudoku? 2's in one of these two. Can I not place any digits? 4's in one of these two. Oh, sorry. These two 4's look up. Okay. That places this 4. There's got to just be more like that. 6 is placed in this box here. We have these two 6's look up. Puts the 5 there, 3 and 6. That's not a 3. This is 1, 4, 5. This can't be 1 or 4. So this is 5, 1, 4, 5. These digits, we do need a 1. We're just going to go on one of these. Oopsie, one of these two. We need a 3. We need a 4, which can only go there. That makes that 3. And then we need a 6, which goes there. And that's a 1. Okay. So down here we get the 5. Up here we need the 1 and the 3. Up here we need the 1 and the 2. So that's 1, that's 2. That's a 2 there. This is a 3. That's 1 and 3. These two digits are 3 and 5. That's 5, that's 3. This is 1 and 5, and we're done. All right. Yeah, algebra confirmed correct. All right. That was neat. I just wish I hadn't messed up the algebra a little bit first, but I got there. I was like, that doesn't make sense because that doesn't match my empirical discoveries. All right, cool. Well, very cool idea, Scott. I enjoyed that. How'd you do?